Okay. Last time we covered plates, plate vibrations, and radiation from a plate. Just very briefly, when we talked about the plate vibration, we described the response. Let's start from here. Just a review here. We had expressed the plate with the bending modulus. Actually, this I will write this as a simple beam equation at the moment, times mass per unit area with acceleration, and that is excited by a force. And what we did afterwards is Fourier transform this and write the result in terms of an impedance. This is just Fourier transform of this. Okay, and it was plate bending impedance times velocity equal to the force. Okay, that's basically what we had expressed. And here, K sub B was the free bending wave number of the plate, and that was a frequency-dependent quantity. Now there were a couple of things that we did. One is what happens to the impedance if you have damping in it. This one does not have any damping, and we said for damping, we write Young's modulus as a complex quantity and define it as, what is that we use, delta? Yeah. And as a result, since bending modulus includes or directly depends on Young's modulus, we have this expression. And when you substitute it in here, then the plate impedance becomes okay. This is the damping related term. Okay? I'm going to give you an example of what that is. You see these. There's no difference between the two bells, basically. Okay? But you can see the difference between the two, what happens. This one has nothing really on it. This one has a coating, okay, that causes damping. You can see the stark difference between the two, what damping means. Just a little bit of damping on this. You can just look at it and see what the difference is. Interesting, right? That's engineering, okay? That's exactly what we mean by when you put a damping or damping coating, you can pass it, damping coating on materials that radiate. You can have a bell, and if you spray it with this coating, it just prevents it from radiating sound at its resonance. But that's particularly true because where does damping become most effective? At resonances. So the first one you can hear ringing, meaning at resonance it's just radiating sound. Second one lowers that amplitude quite a bit. Okay. So this is basically the expression for plate vibration. Now, let's leave that there, and now we're talking about, all right, if plates are vibrating this way, how do they radiate sound? Okay? Sound radiation. This is the bad one. And in terms of sound radiation, we said, okay, now these are the, let's look at this here. This is the forcing function, if you remember, okay, in space, and this is in time. So when we look at this, we say, okay, for a given wavelength or wave number for a given frequency, okay? So you do solve it for each and then synthesize them through inverse Fourier transform to get spatial response of, let's say, in this case, plate. So what we do is let's just take one bending wave, okay, and take a look at what the behavior is, which is what we did before. This is the plate in the z direction and in the x direction. Radiation would be in either direction, in z, and x is how the bending speed travels in the x direction. And here, the way we approached the problem was, we said, okay, here's the sound pressure. Sound pressure must have an x, z, and t component, or in the frequency of wave number domain, okay, in the Fourier transform domain, that would be the response. And it would have a shape, an amplitude and a shape that shows radiation kz in the z direction, k sub x, x direction, and of course omega t. We know that's what it has to be. Okay, this is just a repeat of what we did last time. In this, what I want you to remember is this is a given. That's the forcing function. So in the plate, as the wave is traveling, that's a given. Now the question is, what is kz? Okay, we determine kz from the wave equation and from the boundary conditions. So the next thing we did here was determine the amplitudes. One thing we do is use a, let me do it here, use a boundary condition. And the boundary condition is the velocity, normal velocity at the surface of the plate should be equal to the plate's velocity at that point. And in terms of acoustic variables, acceleration in z direction. Why isn't it in x direction? Why are we not using a boundary condition that's in the x direction, but only in the z direction? Okay, let me ask the question. Why do we not use this? This is T. This is acceleration and extraction. And the gradient. Say again? Yes, this is what we do. But why don't we do the tangential? We can't measure it, and we don't also know it. It's not just the inability to measure, but we don't have a good relationship there, okay, in the tangential direction. As this thing moves up and down, we don't know what is happening to the particle velocity, so we do not use this. Okay? Okay. That's the velocity. This is for the particle. It's not yet boundary condition. This is just for the particle in an acoustics relationship. And the boundary condition then would be particle velocity in the z direction, but evaluated at z equals 0, meaning on the surface of the plate is equal to the plate vibration. Some sort of an amplitude. Okay. So this essentially gives us a relationship between amplitude and pressure. Okay. So from here, we have a relationship between pressure and plate velocity amplitude, and that was and let me write it just a little bit differently. I'm going to do it right here. Okay, where? Okay. This is slightly differently expressed than last time, but nevertheless, kz over k. Here, what we're doing is dividing it by c and multiplying it by c. And of course, omega over c is k. So what we have here is a dimensionless number, kz over k, wave numbers. Rho c is the specific acoustic impedance of the fluid, mv0. Once again, this relationship gives us the value of the pressure amplitude based on v0. But we have to use one more relationship. And the second relationship is the wave equation. See, we started out with this expression. We learned this, but we still are not sure about what kz is. We don't know what kz is. Okay, let me just emphasize this, because this is the way you solve some of these problems. Let me clean the second one. In this case, okay, we say fine, pressure expression has a spatial distribution. That's, it radiates in the z direction, it also has an x component, and it has a frequency component, omega, and an amplitude. Okay, what do we know here? We must know, to begin with, kx, because for a given vibration wave number, what is the sound radiation. The two quantities we want to find out are these, amplitude and Kz. Amplitude we find out by applying the boundary condition, okay, boundary condition on the surface of the plate. The next thing we do is find out what happens to the, how we find the wave number in the z direction, and that's from the wave equation. Because a pressure expression must also satisfy the wave equation, and wave equation was del x Laplace Cn okay. And if we transform this, that is going to give us kx squared, kz squared, okay. Do you have any questions? If you're not following, yes.
How do we find V0? Is it to measure?
I'm sorry, which one?
P0.
P0, V0. V0 is the amplitude of the plate. It's a given. What we're saying is, here you have a plate that's vibrating. At an amplitude. So that's a given. So if you have a plate that's vibrating, what will be the sound radiation? That's what it is. So this is a given. And as a result, we find this. But we still don't know Kz. And that's to find that we are saying and we are requiring the pressure expression to satisfy the wave equation. And from there, you have a relationship. And so from here, we must have so we now finally have the expression for wave number in the z direction. And this is where we found the important relationship about what can radiate and what cannot radiate. You can take a look at this here. If Kz is a real number, then of course you have this radiation. If Kz is imaginary, then what happens? Sorry? Evanescent wave, yes, it just decreases as if it's an exponentially damped property, okay? And so let me just continue down here. If K is less than Kb, then you have Kz, an imaginary number. And what does that do? That gives us a pressure minus Kzz. Okay? So as you go away from the plate, the amplitude will just decrease immediately. So sound doesn't propagate, energy doesn't propagate to the far field. All right, that's the radiation from a plate without taking into account the load of the radiation, because the force that the radiation generates is also acting on the plate. And how did we manage that one? Okay. Let's see. I'll just say here, this is again just a summary, so effect of acoustic loading. Another way this is sometimes expressed is fluid structure coupling. So when you face some of these problems, you can see this in different names. It's exactly the same thing. Once again, what we do here is we have, as before, just the plate impedance, bending wave impedance, and plate velocity, okay? And that is forced by some sort of a external force. Let me, just to be complete here. Okay? But if there's a force that's acting on it due to the pressure, we do also include here kx, 0, and omega. 0 is wave number evaluated at pressure evaluated at the surface of the plate. Why is it negative? Why isn't it positive?
It's opposite.
Exactly, right? It's just simple geometry. It's pressure here. Common confusion is, well, if the sound is going up, why is it negative? Well, sound may travel, energy may travel, but pressure is a scalar quantity. Okay? So here, it's pressuring. It's just like a balloon. You put pressure in it, it forces it in a particular direction. So pressure is adding from here. What we will see in a few minutes is what happens when there's radiation from this side, from both sides. Then you're going to have pressure pushing it up. Okay? One coming from top, one pushing from the bottom, which is what I'm getting to slowly here. Okay? So this is now we have a pressure expression. And how can we express the pressure expression looking back here? Pressure is related to the velocity. Okay? So if we substitute that by the radiation impedance, okay, and the plate velocity, then we have ZB radiation. Okay, so response of a plate now depends on the combined impedance, radiation plus the bending wave impedance of the plate. Okay. And in terms of these, we talked about what coincidence frequency is and what critical frequency is. Do you remember what they are? Coincidence frequency is when the plate wave number is equal to the radiation wave number. Okay? That's the coincidence frequency. And critical frequency is the lowest number that it can achieve. Let's talk now, move on to the new topic about what happens. This is radiation from a plate. What happens if there's a sound wave that's coming onto the plate? Okay? That should be interesting. What will happen? How can you model this? Now you know everything I know about the subject. Okay? How would you model this? Reflection and transmission of a plane wave from an infinite plate. What would you do? Think about this. Reflection and transmission, just like before. Let me clean this up. I'm going to try to remind you from your previous studies. Remember now, you had between two fluid layers, sound pressure coming, sound pressure reflecting, and sound pressure transmitting, right? You know about all these. And you know the incident pressure, reflected pressure, transmitted pressure. We have a particular wave shape coming at an angle that, so you model it as x plus, well, actually, if this is z, this will be minus, and so on. You do exactly the same thing. What is difference is what happens here, the boundary. Okay? Think about this just for a moment. Scratch a few notes. See how you might do it. Instead of having two fluids with nothing else in between, now you have a plate. Okay? You have a plate. You can have two separate fluids, or you can have the same fluid. Just for simplicity right now, use exactly the same thing, okay? Same fluid on both sides, but now you have a plate. How would you model it? See if you can try it. First, the standard approach, which is writing the expressions for what we would expect. Incident, and some sound will be reflected, and some sound will be transmitted. What does it mean, sound is transmitted in this case? There's a plate, a metal plate in between. Literally what that means is this sound has to vibrate. Okay? If this sound does not vibrate, there's no transmission. Okay? Now, when we say sound vibrates, why does it vibrate? Because of pressure. If you come back and look at here just for a moment, it's acting like a forcing function. Okay? Are you guys looking just for a second? When you look at this, just for a moment, the sound that's coming down at it is acting like a forcing function. Okay? So this forcing function is causing it to radiate, okay, which comes back and also loads it, and also transmit, which does the same thing. So let's write all those equations. Number one, the pressure for z larger than 0, and meaning above the plate and under the plate. Above the plate, it has two components. Okay, incident and the reflection. This is above the plate, and for transmitted sound we have only the transmission away from the plate itself. This is the form, okay? There are several things we do not know here, okay? What we do not know is the amplitude of the reflected sound, amplitude of transmitted sound, okay? But we know pretty much everything else. But we said that the plate now is plate vibration. And look, we said plate vibration we know, but we do not know in this case, right? Because you have to find the plate vibration. Because the only thing we know here is sound is coming, okay?
We know the relationship between pressure.
We know the relationship, so we have to find out what that is. And that plate vibration, it will be a result of all of this acoustic field, because we don't know what that is yet, yes. And that's really what we're trying to find, along with the amplitudes of transmitted and reflected waves. So let's say the displacement amplitude is EIKX x minus I omega t. This is the displacement amplitude, and this is the last of the unknowns, the amplitude itself. Okay. This is the first stage of what you do when you're given a problem like this. Okay, write down the forms of the expressions for all the variables in the system. Okay. Pressure expression, okay. Any questions on this? Straightforward. I think several of you were able to write this down. The next thing you do is, except you, next time he will write it. Okay. He's not a very good friend, is he? Okay. The next thing we do now is, logically, you have force, you have a displacement, we write the equation of motion for the plate. Okay. Equation of motion of the plate. And that becomes what? Plate impedance times velocity. Or plate impedance, velocity is what now? If I write it, minus I omega A. Okay, I'm dropping all the variables because this has to be the same for everything. And this is now, let's see. Let's not confuse everybody here. This is, what would you write here? How would you express the force? Impedance times velocity must be equal to the forcing function. How would you express the forcing function? Just give me expressions.
From difference of the pressures.
Right, right. If we call this pressure on the plus side, pressure on the negative minus side, just using those. This is pushing it in the positive direction, okay? and this is in the negative direction, but it's all evaluated at the surface of the plate. And we're assuming the thickness is negligible. Otherwise, you would have to do this as h 1/2 plus minus, okay? But because it's negligible, the thickness of the plate, we use it as 0, okay? If the plate thickness is important for very, very high frequencies, then you would evaluate it, take the plate surface, one here and the other one here. But that's not appropriate for this case. For ultrasonic frequencies, etc., that would be important. Okay, and what are these? If you look at up here, then you have transmission minus incident and reflected amplitudes. Okay, we're dropping these because this is 0. Kx omega t, kx omega t, kx omega t, they're all the same, so we're not even writing. So we have now an expression for okay. This is, as we said, equation of motion for the plate. What else do we know here? And we need? Yes? You need something else, but you also do know something else because there are 3 elements, 3 unknowns that we have. What are the relationships? What do we know? Not the wave equation, but first of all, before then. Exactly, right? Velocity. Particle velocity has to be equal to the normal velocity of the plate, but on both sides. So you need to write the velocity expression for both sides. So here the boundary condition, velocities must be equal. So I omega A, which is the plate velocity, must be equal to the particle velocity on both sides. K1x over K divided by rho 1 C1. Yes? How? Just to keep it as general, for now. We'll reduce it in a minute, yeah. Just to keep it general so that next time you face it, you know what to do. I just want to separate them to show, to trace transmitted and incident, yeah. Okay. Let's just consider the relationship between plate and the particle velocity above the plate, okay, in the z positive direction. And here, you remember, we did drive this expression at the very beginning of this lecture. Are you familiar with this? Does this make sense to you? Do you understand where this comes from? Any problems? You don't understand or no problem?
No, I understand.
You do? Oh, okay. Yeah, you're following. Because I just jumped a step. That's why I want to make sure you're not missing anything. And this is, of course, Pi plus PR. What I want to do is just a simple mathematical convenience. Okay. Add and subtract the incident pressure amplitude. And that gives us Pi plus PR minus 2 Pi. You know why? This expression here okay, the forcing function. What I'm trying to do is substitute for this an expression in terms of the plate boundary condition. And so we're writing this as in a simple form, and we say no, this is something not right here. These are not x, but z. Sorry. Because the velocity is in z direction. Let me correct this in my notes also. Z. Z. It should be all z. Yeah, because derivative is with respect to the z direction, okay? K1z. Okay. If we now substitute it back here, okay, we have minus I omega A ZB now, transmitted pressure expression we can also write that. Okay, let me come down here. Okay, and substitute it one more time. Actually, I could just put it here. You can substitute. Well, let me just leave it because it's going to confuse. Let me see, there may be, I want to check the signs just for a moment. I think there's something, it's not quite right. Let me just see.
First should be plus minus I omega A.
First, which one?
That's
Right here? This should be plus, you say? Let me just see. Mm-hmm. Yes. It should be that. Yes, all right. Now it's correct. Okay. All possible. Just make sure we're not missing anything here. Okay. These are the radiation impedance. Okay, so we can call these as, let's say, Z1 and Z2. And let's see, do I need this here? Yeah, I want to leave that there. Plate velocity. Okay? So twice the incident pressure amplitude, impedance, combined impedance of the plate, mechanical impedance of the plate, radiation on one side, radiation impedance on the other side, times the velocity of the plate. Now, if you go back and look at each one of these, impedances. So let's see. You'll see the familiar expression that we had from before. And similarly, okay. Now what this gives us, let's see now, where did we start? What this gives us are relationship between the incident pressure to a plate and the radiation or the vibration amplitude also of the plate. So sound is coming at it, reflected and transmitted, and vibrates the plate. And why do we need to know it? In cases like I mentioned last time, nuclear power plants, for example, okay? Vibration amplitude due to acoustic resonance, for example, in the cooling fluid is very important because high stresses can actually lead to failure. So these are numbers that are very important in some of these applications. Now, with these amplitudes that are given, we can now write the expression for transmitted sound. The transmitted sound will be, as we have briefly written it before, e to the I k and let's see now. Okay. From here, and I omega A is no, sorry. We have already done that. Relationship for transmitted sound pressure. What is the transmission coefficient? Sorry? Okay. It's what? Okay. Yeah. 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 Exactly. Yeah. And what was your answer? Oh yeah, you were reading the whole thing, yes. So no, okay. Okay, so, but there are several things to consider here, right? One is the pressure, which I did not indicate. Pressure transmission coefficient. Then, of course, there's the power transmission coefficient. I think our tape is running out, so let's take a few minutes break. Okay, and when we come back, we'll cover these transmission coefficients and see if we can review this, because I think we have a whole picture here, and it's an approach. How do you approach to solve a problem like this? It applies to spheres, shells, etc. It doesn't really matter what the geometry is. Okay, 2 minutes. It's getting warm in here.